Hello and welcome to Controllers Tech. We have already covered how to use UART in ESP32 using the blocking mode. We also learned how to control the LED on the ESP32 by receiving commands from the computer. Blocking mode works well when you are handling small amounts of data, but when the data size becomes large, it can delay other tasks and prevent them from running on time. Because of this limitation, today we will learn how to use UART in interrupt mode. In this video, we will mainly focus on receiving data using interrupts, and we will test it by sending large amounts of data from the computer to see how the system behaves. Before I begin, I would like to give a shout out to Robert Johnson for joining the Patreon membership and supporting the channel. If you would like to support this channel, help decide the topics of upcoming videos, and receive exclusive updates about the projects I am currently working on, please consider joining the Patreon membership. You can find the link in the description of this video. Alright, let's now open the Espressif IDE, and create a new project. Make sure to check the option to create the project from templates. Search for UART, and you will find an example related to UART events. Rename the project as you prefer and click Finish to generate the project from this template. Here is the main file of the project. It contains two functions. One is the main function, of course, and the other one is used to handle UART events. If you run this file as it is, it will work properly. However, instead of running it directly, let us first understand what this file contains and how it works internally. First, inside the main function, the UART peripheral is initialized with a baud rate of 115200, 8 data bits, no parity, and 1 stop bit. Then the UART driver install function is called to install the UART driver and allocates the required RX and TX buffer sizes. After that, the UART param config function is used to configure the UART parameters according to the selected settings. Next, the UART set pin function is called to assign the appropriate GPIO pins for TX and RX. There is also a separate function for enabling pattern detection. During data reception, if the plus symbol is received repeatedly 9 times in a row, a specific interrupt is triggered and a corresponding event is generated. This feature is known as pattern detection. You can configure the pattern based on your own requirements, but in this tutorial, we will not go into the details of pattern detection. The xTaskCreate function is then used to create the UART event task. This task is responsible for handling all UART-related events generated by the driver. Here is the UART event task. At the beginning of this task, there is a queue that waits indefinitely for UART events. Until an event is received in this queue, the remaining code inside the task does not execute. Once an event is received, the code checks the event type. You can see multiple cases in the switch statement, each corresponding to a different UART event. Let us go through them one by one. First, we have the UART data event. This is the primary event that we will focus on in this tutorial. The data event is generated when the RX ring buffer receives data from the UART driver and certain configured conditions are satisfied. These conditions could be: the FIFO threshold has been reached, or a timeout has occurred. The UART FIFO has a total size of 128 bytes, and by default, the threshold is set to 120 bytes. So when 120 bytes are received, the data is transferred from the FIFO to the ring buffer, and an interrupt is generated. As a result, the UART data event is triggered. In another situation, if fewer than 120 bytes are received but a timeout occurs before reaching the threshold, the UART data event will still be triggered. In the default example code, the received data is simply read from the ring buffer and transmitted back through UART, effectively echoing the data. Next, we have the UART FIFO overflow event. This event occurs when the FIFO memory overflows. In such a case, the ring buffer is flushed, and the event queue is reset to recover from the error condition. Then we have the UART buffer full event. This event is generated when the ring buffer becomes completely full. Similar to the previous case, the ring buffer is flushed and the event queue is reset. There are additional events such as break detection, parity error, and frame error. However, handling these events is not required for this tutorial. Next is the UART pattern detect event. This event is triggered when the configured pattern is detected, for example, when the plus symbol is received 9 times consecutively. As mentioned earlier, we are not going to cover pattern detection in this video. So this is how the ESP-IDF manages and handles UART events internally. Now, I will remove the parts of the code that are not required for this tutorial and modify the remaining sections according to our specific requirements. Don't worry about this fast forward, I will still explain the remaining things. Let's start by selecting the UART number. The ESP32 provides 3 UART instances. In this tutorial, I will use UART2, just as we did in the previous UART videos to keep the configuration consistent. Next, we define the TX and RX pins. UART2 TX pin is GPIO17, and the RX pin is GPIO16. The connection diagram remains the same as in the previous video. The ESP32 RX pin should be connected to the TX pin of the USB to UART module. Similarly, the ESP32 TX pin should be connected to the RX pin of the module. UART communication always requires a cross-connection between TX and RX lines. The buffer size is configured to 1 KB, and we will keep this value unchanged for this tutorial. The UART queue is already defined in the example, but since this queue is specifically used for handling UART events, I will rename it to event queue to make its purpose clearer. Now, I will define a structure for the UART data, that contains the pointer to the data, and the length of the data. This structure will be sent through another queue from the UART event task to a separate processing task. That is why I have defined this data_queue. We will create a dedicated processing task that runs only when data becomes available in this queue. This helps keep event handling and data processing separate. Now let's modify the UART data event. When the UART data event is triggered, it indicates that new data is available in the ring buffer. First, we define an instance of the UART packet structure to store the data received from the ring buffer. Then, we dynamically allocate memory to store the received data. You might ask why not define the buffer globally. If it is global, the same memory can be overwritten by new data before the previous data is processed. By allocating memory dynamically, each received packet gets its own space, making the system safer and more reliable. Next, we call UART read bytes to read the available data from the ring buffer and store it in the allocated memory inside the structure. The function returns the number of bytes read, and this value is stored in the length member of the structure. At this point, the structure is fully prepared, and we send it to the data queue using xQsend. We are not making any changes to the FIFO overflow, buffer full, break detection, parity error, or frame error events. That completes the required modifications in the UART event task. It now reads the incoming data and forwards it to the data queue for further processing. Next, we create another task called the UART process task. This task is responsible for processing the received data. Inside this task, we again define the UART packet structure to hold the data structure received from the data queue. Within the infinite loop, the task waits indefinitely for data from the data queue. When data becomes available, it is received and stored in the packet structure. For testing purposes, I will send this data back through UART, which means whatever you send from the computer will be echoed back. However, in your own project, you can process this data in any way that suits your application. After processing the data, we must free the allocated memory for that data element, since it was dynamically allocated earlier in the event task. This step is important to prevent memory leaks. Now let's move to the main function. We will keep the default UART initialization settings, but we will change the UART number accordingly. The RX buffer size, which is the ring buffer, is set to 2 kilobytes. Remember, the FIFO size is only 128 bytes, but the ring buffer must be large enough to hold the incoming data. Do not make the buffer too small or unnecessarily large. Select a size that matches your application requirements. The TX buffer size is also set to 2 kilobytes by default. If the TX buffer size is set to 0, the transmission will operate in blocking mode. Therefore, make sure to define a proper buffer size if you want non-blocking transmission. I will reduce it to 1 kilobyte. The event queue size is set to 20, which means it can hold up to 20 events at a time. There is no need to initialize it separately because it is automatically created inside the UART driver install function. Next, configure the parameters for UART2 and assign the TX and RX pins. RTS and CTS pins are not used in this configuration, so leave them to no change. There seems to be some issue with the RX and TX pins we defined earlier. Let me change the pin definition to just 17 and 16. The error seems to be resolved at the moment, but we will confirm this after building the project. Now, once the UART initialization is complete, create the data queue with 5 elements. This queue will hold up to 5 UART packet structures. Finally, create the UART process task using xtask_create with the following configuration. Task function is the UART process task. Keep stack size to approximately 2 kilobytes, with no parameters being passed to this task. Keep the priority lower than the event task, and no task handle is required for this task. That is it, our project is now ready for the test. Let's build the project once to check for any errors. There are no errors in this project, so let's flash the program to the ESP32 board. Now open the serial console and connect to the USB to TTL port. First, let us send a small amount of data. The data is being transmitted from the computer, but the ESP32 is not sending anything back. If you look at the ESP32 logs, you can see that it keeps restarting continuously. Let me disconnect the serial console so we can clearly observe what is happening. The log shows that the XQ receive assertion is failing. This indicates that there is a problem related to a queue. In this project, we are using 2 different queues. However, if you look closely, the event queue with 20 elements is created successfully without any issue. This clearly suggests that the problem is with the data queue that we created separately. Since the reboot happens immediately after startup, it means the queue was not created properly in the first place. And here is the exact reason. The data queue handle was not assigned correctly when the queue was created. Let's correct the handle assignment here and then flash the project to the board once again. Now, when we send small data, it is transmitted and echoed back correctly. Keep an eye on this send and receive count. It will track if our data transmission is successful or not. Let's move on and test with large data. Here, I am going to copy an entire post from my website. I will paste it into the send section so that we can transmit it to the ESP32. To confirm whether the entire data is received successfully, we can verify the starting and ending parts of the transmitted text. The data starts with the line, in part 1, we built an I2C scanner. And it ends with the line, I accept the privacy policy. I do not know the exact size of this data, but let us transmit it anyway and observe the result. The transmission is now complete, and you can see that the send and receive counts are exactly the same. The computer sent 30,396 bytes to the ESP32, and the ESP32 processed and sent back the exact same number of bytes to the computer. We can verify the integrity of the data by checking the beginning and ending lines. The received data starts with the same line. In part 1, we built an I2C scanner. And it also ends with the exact same line, just as expected. This confirms that the ESP32 successfully received the entire data, and echoed back the same amount without any loss. Now let's increase the data size further. I am adding the same data again in the send section. So now we have approximately 60 kilobytes of data to test the transmission. Let's send it. You can see that the ESP32 has once again sent back the exact same amount of data. This clearly confirms that large data transmission is working properly. You may notice that UART data events are triggered after every 120 bytes. This is because the default FIFO threshold is configured to 120 bytes, while the total FIFO size is 128 bytes. When these 120 bytes are received, an interrupt is triggered, the data is transferred from the FIFO to the ring buffer by the driver, and the UART data event is generated. At the end of the transmission, if fewer bytes remain, for example 26 bytes, and the threshold is not reached, a timeout occurs. This timeout condition also generates a UART data event. So, UART data events are generated in two situations, when the threshold is reached, and when a timeout occurs. In both cases, the available data in the FIFO is moved to the ring buffer by the driver, and from the ring buffer, we read it into our own buffer for processing. This is how we efficiently manage and handle large amounts of data using UART events in ESP32 with ESP-IDF. ESP-IDF does not provide separate user-level control for UART DMA. The driver internally uses hardware features to move data efficiently. If you require complete and low-level control over DMA, you would need to implement a custom UART driver. However, this is usually unnecessary unless you are working with extremely large and continuous data streams, such as video data from a camera. For most practical embedded applications, this approach is more than sufficient and reliable. So that brings us to the end of this video. I hope you clearly understood how to use UART events in ESP32. You can download the complete project from the link provided in the description of this video. If you have any doubts, feel free to leave a comment below. Keep watching, and have a nice day ahead.